Okay, we are starting Unit 5, Lesson 2, which is the basics of hypothesis testing. Probably the most important lesson we have left in this class, as the next two full units will be on hypothesis testing, and this lesson is going to give us a structure for how to do all those lessons. So, what we're going to learn in this lesson is just the basic idea of what is a hypothesis test. And then each of the following lessons will dive into a specific type of hypothesis test, but it's going to be very important that we understand the structure, which is what this lesson is going to bring. So, this is the hypothesis test method. There are different ways to do hypothesis testing. We do a method called the p-value method, and we're going to use that method for all of our problems for the next two units. When I say p-value, that is not related to proportions, the thing we learned about in the last notes. It's its own thing altogether. So, in every problem we do, for at least the rest of this unit, we're going to start by identifying our null hypothesis and our alternative hypothesis. Some kids call this the ho and the ha, but the technical terms are this is the null hypothesis and this is the alternative hypothesis. This is called the hypothesis testing method. So it's really important to set your hypotheses first. Then we're going to learn about something called alpha. Then we're going to find a test statistic. Now that changes from lesson to lesson how you find the test statistic. Then we're going to find a p-value, which is why this is called the p-value method. And then we'll decide whether or not we're going to reject the hypothesis or not reject it. And then finally, we're going to put our conclusion into words at the end. So let's break down each step. The first step is identifying the null and alternative hypotheses. This is what gets the ball rolling for the whole problem. So H sub 0, or pronounced the null hypothesis, is the accepted value that's going to be challenged by the test. So we're always going to write this in some form of an equation. It's always going to be something equals a number. Sometimes that something is going to be a proportion value. Sometimes it's going to be a mean. Sometimes it's going to be a standard deviation. It could change from problem to problem. It's always going to be a parameter. We're always talking about the parameter here, where we are making a prediction in sorts of what the parameter will be. So the null hypothesis is kind of what we assume is true. So something like the probability of having a baby girl is 50%. That would be our null hypothesis. Is that, yeah, it's 50%. That's what's normal. The probability or the proportion of babies that will be girls is 0.5. Now, the alternative hypothesis is always going to be an inequality. This is going to be an argument of something new that we think is true. So it's accepted that we think this is true, but we're going to try to prove that instead, maybe the probability is greater than 0.5. Maybe it's less than 0.5, or maybe we're just trying to show that it's not 0.5. And that's what we're going to try to prove with this test, is that the alternative is actually true. We're assuming that the null is true, but we're going to try to show that the alternative is actually what's true instead. So let's do a couple of examples. The Microsort, or really just one example, the Microsort company claims that their product increases the probability that you'll have a baby girl. If we are trying to test this claim, what should we set our hypotheses as? So the claim is that their product increases the probability that you'll have a baby girl. Well, we need to set up a null and an alternative hypothesis right now. Well, the null is what should be true. Not what they're claiming, but what should be true. And what should be true about having a baby girl is that should happen 50% of the time. So we're not talking about a mean here. We're not saying, how many baby girls or anything like that. We're talking about what percentage or proportion of the babies should be girls. So that's going to be a P, and we're going to set that equal to 0.5. This is always going to be equals in the null. It's always going to be an equal symbol. Okay? This will always be one of our parameters, which will either be a mean or a proportion value. Okay, so this will be a parameter. So we're not going to use p hat here or x bar. We're going to use a parameter. So p or mu or sigma. We're going to use one of the formal parameter notation letters. Now, for the alternative, we're going to rewrite the outside again. So we're going to still be talking about p, and we're still going to be talking about 0.5. But the claim is that they will increase the probability of having a baby girl. That means that they want the probability of a baby girl being greater than 0.5. So we're always going to put an inequality symbol here. Okay, so we'll make a little mark. This will always be an inequality. So either a greater than, a less than, or a not equal to. So these would be our hypotheses. The null is that the probability of having a baby girl is still just 0.5 when you're using this method. The alternative is that the claim is that they're actually increasing the probability. So the probability is actually greater than 0.5. Now, moving on, we're going to talk about setting an appropriate alpha. So you have to know what alpha is, and that's a significance level. So alpha represents the probability of what's called a type 1 error. And this is when we reject a hypothesis that's actually true. So at the end of this whole problem, we're going to either reject or fail to reject our hypothesis at the beginning. And we want to make sure that our chances of this type 1 error are really low. So if we let alpha from the beginning of the problem, if we let alpha be 0.01, that says we're willing to risk a 1% chance that we're going to say the null is wrong. So we're going to reject the null, which, like, if you look at the last problem, the null was that the probability of baby girl is 0.5. If we reject that, we're going to say that this is true instead. So if you let alpha equal 0.01, we're saying that there's a 1% chance we're going to reject that null and be wrong. So we can't be certain that our answer is going to be correct, but if alpha is 0.01, we're setting a limit saying that at most we're willing to accept a 1% chance of being wrong. We could also use an alpha of 0.05. This would be saying that we're willing to accept up to a 5% chance we're going to be wrong. This is not a big deal because there's still a 95% chance we're right in our conclusion. But we want to decide what alpha should be based on the severity of the impact. So if you think about that last problem when I was talking about the likelihood that this microsort method will work to increase the probability of having a baby girl, that's not really life or death. If you end up with a baby boy, it's not the end of the world. It's not that big of a deal. So in that kind of problem, we would probably use the 0.05 alpha. Now, if we were maybe testing the blast radius of a bomb, and we're trying to make sure that the bomb isn't going to expand too far where it maybe hits a school or something serious where we're dealing with life or death, we would probably want to use this alpha of 0.01 because we don't want to be wrong. So we want to lower the chances that we're wrong. And that's what alpha equals 0.01 would mean. So I kind of jumped the gun on that example, but a statistician is testing the claim that the blast radius of a bomb is less than 1 square mile. In this case, I would be setting alpha to be lower, 0.01, meaning I'm willing to risk a 1% chance that I'm wrong. The second one talks about testing the claim that the probability of a student graduating high school is greater than 90%. So it's not a big deal if I get this wrong. We always want our answers to be, confident and sure that we're right, but it's not a big deal if I get this one wrong. So I'm willing to risk a 5% chance that I show that it's greater than 90, but it actually isn't. I'm willing to risk a 5% chance of that because it's not life or death. So we're going to set our hypotheses. Then we're going to set an appropriate alpha, the chance that we're going to be wrong in the end. Okay, and now we're going to get into our test statistic. So this is really where the next 3 lessons will branch off. In order to do the methods that we're going to do, we have to go find what's called a test statistic. For proportions, we're going to use this, the z-score, and it's a special formula for that z-score. For means, there's going to be 2 different test statistics we could use. One of them is actually the central limit theorem. This is actually the CLT from last unit, and we'll use that in some circumstances. And then there's this other thing called the t distribution that you haven't learned about yet, and that is the test statistic that we'll use for other mean situations. That difference will get broken down when we get into lessons 4 and 5 later in the unit. So for our notes, what we're going to do is we're going to set up a test statistic for that microsort example that we already found the hypotheses for. Remember, we found the hypothesis that the null was that p equaled 0.5. The sample, so now after we set our hypotheses and we've set our significance level and all that, we're now going to have to go get data. Most of the time the problems are going to provide the data for us, which is what this is. This is data that we've collected to go test this hypothesis. So the data we collected showed that 13 out of 14 kids whose parents used this product ended up being girls. So a vast majority of the kids born using microsort were girls. So what we're going to try to do is we're going to try to go and determine whether or not this proves that the probability of having a baby girl is actually greater than 0.5. So because this is a proportion problem, we're going to use this sample statistic, which is z equals p hat minus p divided by the square root of pq over n. So what we need to do is we need to go figure out what these different letters are. So p hat is the sample proportion. So not the p from the beginning of the problem, but the actual sample proportion, which we'll find right here, 13 out of 14. So z is going to equal 13 divided by 14 inside these parentheses minus p. Well, the whole point of a hypothesis test is to assume that the null is true, work out the math, and show that if the null were true, we would get a really crazy result, which is something we've talked about throughout the semester. So even though the test statistic really suggests that it's not 0.5, we're going to assume p is 0.5 from the null hypothesis. So we're going to use whatever p we had in the null hypothesis, which is 0.5. Now we're going to divide this by square root of that same p, which was 0.5. And now remember, q just equals 1 minus p, so that's also going to be 0.5. And then our sample size is this number right here, the 14 kids in the sample we used to collect data on this. So n is 14. So we're going to be really careful about how we type this into our calculator to go get z. We're going to type parentheses around the 13 divided by 14. We're actually going to do big parentheses because there's a numerator. So we're going to do big parentheses here. So it's going to be open parentheses, another parenthesis, 13 divided by 14, close parenthesis, minus 0.5, close the big parenthesis. So where I just was right here, closing the big parenthesis. Now divided by the square root of, and now I've got to do all of this down here. 0.5 times 0.5 divided by 14. And once I have all that typed into my calculator and hit enter, I get back a z-score of, so I'm going to write it like this, z equals 3.21. If you're having any problem getting that number on your calculator, just reach out to me and I can walk you through it a little bit slower if you need. So that was the test statistic. So we set our hypotheses at the beginning. We picked an appropriate alpha, which for the microsort problem, I would certainly be using 0.05. It's not that big of a deal if we get it wrong. Then we calculated the test statistic for that microsort problem. Now we're going to determine the p-value. So determining the p-value is going to require us to draw a picture. It's a little complicated in terms of, you see, there's a lot of notes on how to do this, but I think you're going to catch on to it pretty quick. So a p-value is the actual probability of us being wrong if we reject. So we talked earlier about alpha. Alpha was how much we were willing to be wrong. The p-val is how much we are actually risking of being wrong. So we've already set in this problem a 5% limit on how wrong we're willing to be. We're willing to risk a 5% chance we're wrong. The p-value calculation is actually going to tell us how likely it really is that if we reject, we'll be wrong to reject. Okay, so here's the rules. Okay, if the alternative hypothesis was a greater than, then we're going to go to the right. And I'll show you what this looks like when we do our example. If it's a less than, we're going to go to the left. This next part is where it gets a little confusing. And we'll break this down further in the next couple of notes, the next couple of lessons. But if it's a not equal to, then what you have to do is you have to either go to the right if it's positive or the left if it's negative, and then multiply by 2. So that's a little bit complicated. If it's a not equal to and it's positive, you're going to go to the right and then multiply by 2. If it's a not equal to and it's negative, you're going to go to the left and multiply by 2. This will make more sense when you see some examples. So if you're a little confused by that, don't worry. The bigger thing to understand in this lesson is this rule. If the alternative is greater than, we're going to go to the right. If the alternative is less than, we're going to go to the left. That's the big thing to know for this lesson. So remember, we got a test statistic of z equals 3.21. If we're talking about z, we're actually talking about the normal distribution from last unit. Remember, the middle of a normal distribution is 0 for z. Z equals 0. So we're looking at 3.21, which is going to be way over here. And we want the area to the right of this 3.21. And it's going to be done the same way we did it last unit. We're going to go normal CDF. And then we're going to type in 3.21. We're going to go to the right, which is positive infinity this way. But remember, our calculator doesn't know infinity, so we just use the number 10. Comma 0, comma 1. We're going to type that in our calculator and see what we get. And that answer is going to be our p-value. So our p-val, which you really write it like this, p-value. The reason you write it that way is because we already have something called p for proportions. So we need to differentiate it from that, so we call it p-val. So I go to normal CDF, 3.21, comma 10, comma 0, comma 1, and I'm getting back a really small answer. I'm getting back 6.637 times e to the negative 4, and all that means is slide it back 4 decimal places. So this has to go 1, 2, 3, 4 spots back, which means 1, 2, 3 zeros get slipped in. So we're going to write this as p-val equals 0.006637. What I want you to ultimately realize about this is that means that the chance that we're wrong if we reject is really, really low. And let's just think about what this means compared to what we were doing before. It means that if that 0.5 is true, the chance of getting that many girls in 14 births is this low. That's how low of a chance there is of actually getting that many births. So, or that many girls in 14 births. So it's much more likely that the null hypothesis is actually untrue than the idea that we just got a really weird 14 births. So to recap, we found our hypothesis, or set our hypotheses. We selected 0.05 as our alpha. We calculated the test statistic. We used the test statistic to calculate the p-value. Now we have to make this decision. Should we reject the null, or should we fail to reject the null? You never get to confirm the null. You either reject it or you fail to reject it. Okay? So, we set a significance level of 0.5. That means we were willing to accept at least as much as a 5% chance that we would reject and be wrong. Well, our actual p-value for this problem was really small. I just rounded it for this slide to 0.007. That's a really small p-value, which is definitely less than this 0.05. And if that's the case, then we are able to reject, because the chance of being wrong, the p-value is the chance of being wrong, is lower than our willingness to risk being wrong. We were willing to risk a 5% chance of being wrong, and there's only a 0.07 or 0.007 chance of being wrong. So we are going to reject the null. What that means is we're saying we don't believe that p is actually equal to 0.5. Finally, we need to know how to state our answer. So there's really just a script to this. Okay? So we just rejected. When you reject, you're going to just type up this script. There is not, so this is the script right here. There is enough evidence at the, for our case, 0.05 significance level to suggest that, now this is the weird thing, if you're rejecting the null, you're saying the alternative is true. So we're going to put into words saying the alternative is true. If we failed to reject, we would have said there's not enough evidence at the, in this case, 0.05 significance level to suggest that, and again, we're going to put the alternative hypothesis into words. So, final example for us, for the microsort problem. Because we rejected, we would say, there is enough evidence at the 0.05 significance level, you can use SL as an abbreviation, to suggest that. Now, I'm going to go back to the beginning of this whole notes and look at what the alternative was. The alternative hypothesis was this. P was greater than 0.5, which meant that their product increases the probability that you'll have a baby girl. So we're kind of going back to the claim here. They claimed that the product increases, and that's what the alternative meant. And we actually showed that this is not true and this is true. So we're going to put that into words at the end. That Microsort increases the probability of having a baby girl. And that's your script. What I would recommend is having this on your cheat sheet and just using the script. And that's all you got to do. So your homework for this is going to be just kind of breaking down parts of hypothesis tests. I actually think when we get into the real lessons and you do the entire hypothesis test at once and you see it all developing at one time, that you'll feel more confident about this. So if you're struggling and these notes were tough for you, there is a silver lining that the next couple of lessons really are just further practice with this, and you're not going to learn too much drastically new information. You're really just going to get more and more practice at this method that you've been taught here. So hopefully you'll feel better and better at